Hey guys, it's Fernando, and today I want to cover demystifying data science. The reason I want to include this is because a lot of people, when they start data science, they immediately become very intimidated by it. They think it's going to involve doing a lot of math. They think it's going to involve probably they can even wrap their minds around the idea that an algorithm is learning by itself. And today I really want to show that it's very, very simple. A lot of the math is automated. A lot of the value that the data scientist adds is the types of problems and the type of data. Like, how creatively can you clean the data, format the data, what interesting problem can you face? That's the real value. It's not the math, because a lot of the math is automated. And maybe if you want to optimize a model, you might need an understanding of the math behind the models, and you do need it to do data science, but it's not the biggest part. And I want to just show you that at a high level, data science is pretty simple and a lot easier than you thought. And by the way, I found that about this like really late in the game when I finally did a project, and I was like, wow, this is what I was scared about. Okay, so I want to give you an overview of machine learning. Machine learning is basically an input, an algorithm, and an output. An example is an input is images, right, of cats and dogs. You feed it to an algorithm, and then it's going to tell you whether it's a cat or a dog. That's it. So the algorithm in this example had to be trained already to know whether it's a cat or a dog, but it sees the patterns. It sees these pixels are dogs, these pixels are cats. You give it a new set of images that you don't tell it whether it's a cat or dog, and then it tells you whether it's a cat or a dog. That's it. And out of this comes you can come up with three different machine learning problems, depending on the type of algorithm and the type of output. So these are the three problem types. So depending, the algorithm can either be supervised or unsupervised. Supervised is that it needs training data with labels before, like the cat and dogs. Unsupervised is that it doesn't, and then it creates clusters that it sees. It sees its own patterns and then clusters maybe the images together or specific rows together. That's unsupervised. The output can either be categorical or continuous. In categorical, it's images, cats or dogs. Continuous is numerical, price of a house, square feet, temperature. It's like infinite in between, so that's continuous. So let's go. Let's see the specific problem type. So supervised and categorical is this spam problem. So it's supervised because it needs training data. It needs text from mail and then labels whether it's spam or not spam. You feed this to the algorithm, it trains, and then when you give it a new text, it's going to guess whether it's spam. It's not going to guess, it's going to predict whether it's spam or not spam. So it's supervised, it needs training data with labels, and then it's categorical because it's spam or not spam. Supervised continuous is how much should I sell my house for? So in this example, again, it needs training data, square feet of house, number of rooms, and then you give it the price that it's sold for. And then in the future, when you give it a new dimensions like square feet or number of rooms, it's going to predict the numerical value of the house, the price. So it's supervised continuous. The third is unsupervised categorical. In this example, you give it it's customer segmentation. So you give it a data frame with each row is a person, each column's maybe the shows they watched or something behavioral about them, right? If they watched this show, 1, if they didn't watch the show, 0. And then you give it to the model and you say, cluster in 4 groups. Then it clusters it together, and then you analyze the groups. You say, maybe these people are the ones that watch adventure shows. These are the people that watch reality shows. And by the way, this example I gave is because I used to work at Discovery, and these are the type of clustering algorithms, clustering problems you would do. And the last section is unsupervised and continuous. So when it clusters things together, it's going to cluster it into defined groups, 1, 2, 3, 4, 5. It's not going to be a continuous output. So there's not really a type of problem there, but just looking at the workflow, which is input, model, output, you could see how you can come up with these machine learning problems, right? All right, so from these problems, this is basically the workflow for a data scientist. You get data, you put it in the model, whether it's categorical or continuous, you put it in a model, whether it's supervised or unsupervised, and then you optimize it by a metric, right? So in the images example, maybe the metric is accuracy. How many images did we classify correctly, right? Like the model performance is the most important thing. You could see how good the model is. What if it's not as? What if we just picked randomly, right? Images of cats and dogs. Is the model doing better than a random, than just randomly picking one? If not, then the model isn't worth it. But realize that it's just this. It's getting the data, training the model on that data, and then seeing how well it's performing. That's it. And I'm going to show you how you can actually train a model, do this whole process, the whole data science process in 9 lines. It's the next row. So this is the 9 lines, right? This is, I think it's, this is house price data. So I got this from Kaggle, and it's the example, like how much did it sell for, and then like square feet, I picked lot area and year sold. So in this example, in line 1 and 2, we download the packages. Line 4 and 5, I upload the data, I select the data, right? I only pick 2 features, year sold and lot area, and the sales price is the output, and it's continuous. Here, I do a train test split. I train the model. I do an instance of the model, train the model, and then here, I just compare. The benchmark is the mean, and here is my predictions, and I see mean squared error, which is a linear regression metric, and that's it. This is it. This is all of data science. Obviously, this is not gonna get you a job. This is not the best model at all. But at the core, this is all it is. If you were to make it better, you maybe choose different features, or maybe you choose different data and combine it with this and try to increase the prediction. Maybe you pick a different model. Maybe you pick a different metric, but you're still in that data model metric. You're just trying to optimize the metric. That's it. And if you want to optimize the metric, then you got to learn the math. Then you got to say, okay, maybe for mean squared error, we should include these features, or maybe we should transform this data, and so on. But this is it. Don't make it more complicated than it is. Don't start going deep into books before you even do a project, before you actually do these 9 lines. Try these 9 lines first in whatever project you want to do. Investigate for each model, what metric are you trying to optimize. Don't make it more complicated than it has to be. And now I want to give some examples of different types of projects, different types of models, and different types of metrics. So here we have, again, the spam problem, right? That's the problem. The data is text data. The model is naive Bayes. The result is 1 or 0, and the metric is recall. That's it. So you just import sklearn naive Bayes. You get the data, you transform it, you train it, then you get the results and calculate the recall, and then calculate the recall from some benchmark, maybe random or mean. The random. And that's it. Then you just try to increase the difference, or in this case, decrease the error. The problem is customer segmentation. The data is customer behavior. The model is k-means, and the result is 1 or 0. So this is an unsupervised problem. There's no clear metric. The only metric that you're trying to is human intuition. That's the one you're trying to optimize. So human intuition is you're going to look at the clusters that it made and see if they make sense. But an actual metric is also silhouette score. You could see the silhouette score and look at the clusters. I would advise not only to use that, but human intuition. That's the metric you're trying to see. So you see the results, and then you see which one's more intuitive, and that's it. You're just trying to optimize for the metric. Predict house prices. That's the one we had before. The data is house features, the model is linear regression, and the result is house price. And here again, we have the root mean square error, like the lines, and you just pick different models, different features, and you optimize for, you try to lower the root mean squared error. Last one is fraud prediction, transaction data, we have decision trees. The result is 1 if it's fraud, 0 if it's not, and then you can pick recall, precision, accuracy, and just try to optimize for that. Don't make it more complicated than it has to be. This is the core of data science. That's why it's really important to start doing projects. See that this is all it is, right? If you want to get, this is the beginning. I'm not saying you're going to get a job just from doing these 9 lines, but if you want to optimize it, then you got to start learning the math. And you're going to be more interested if you understand what's happening, the whole process. You know, you're not just like learning decision tree for a month. You don't know the metric of optimization. You don't know the type of problems. You don't know the type of data. Just go straight into problems, look at the project guide, and go from there. So yeah, that's pretty much it. I really hope this helped. For me, it took, for a lot of people, don't even, months into learning data science, they don't know this. So I'm excited for you to know this, and I'm excited to see your projects, and I'm excited to see your portfolio and start applying for jobs. All right, guys, continue doing this, and I'll see you again.